Here is part three, where we're going to go over this inclined plane version here. This one is admittedly a little bit more complicated. I've combined 7 and 8 because they really are quite similar in terms of what you need to do. All right, let me just make sure I have this. That's not what I want. I want this. Okay, so um, let's start off by drawing the free body diagram as we have before for both of the blocks. Whoops. So the first one, let's change colors and zoom in just a little bit, is a pretty straightforward. It will be supported by this tension up, and it's being pulled down by the force M times G. Okay, so continuing with the free body diagram for this other one. All right. In this example, in this first version, we're saying that mu is equal to 0. And I know that's going to be the case, but as I go through this problem, I'm going to pretend like there is a mu, and then I'll just show you what it would mean if there isn't, and so on. So I'm kind of doing 8, and then I'll show you 7. All right, so the free body diagram is going to look like this. You're going to have the force of gravity, which is going to be pulling this object straight down, and not Fg. I'm going to write mg here. Okay, it's going to have its normal force, all right, which is going to be perpendicular to the plane. It's going to have this force of tension, okay, that's going to be wanting to pull it up the plane. Now, this question isn't totally clear on which direction this block is moving, but I think it is fair to assume that that this object, because it has the greater, or excuse me, even because it has an equal mass, but it has a greater force in the direction it's allowed to move, that the whole system will want to move kind of in this direction here. It's going to want to move up the ramp. So with that assumption in place, all right, in fact, it's not really an assumption. I'm kind of just declaring it's going to move up the ramp. That means that friction is going to be directed down the ramp, and it's going to look like this. Truth be told, a more in an AP sort of situation, you'll be told the direction the object is moving, or you will be asked to determine it given a certain set of scenarios, right, or certain conditions. So these are the free body diagrams. This is the free body diagram for each one of these objects for this situation, considering that we have a mu. Again, if we didn't have a mu, then this, if we didn't have a mu, then the force of friction wouldn't be here, but we do have a mu, so the force of friction is there for number 8, which is kind of what we're doing right now. All right. Now, the next step here is to find the components of this force of gravity for the object that's on the incline. And as soon as I start to draw on these components, it's no longer the free body diagram. So we have this part of it, which we would, I'm just going to leave it as FGY for right now. It's the portion of this force that's in the direction perpendicular to the motion of the object, okay? So then we have this part of gravity, which we call FGX. And once we have these two forces here, it is as if this other force doesn't exist. So let me just do something right here. So if I do this, right, I can also leave it like that. Once I find these components, it is very much like, again, this force isn't here, and it is very much like this force could be this force could be imagined to be up here, right? We can leave it down there. It's whatever is most comfortable for you. So again, it's very much like it's right here, and I'll draw it slightly offset so it's a little bit easier to see for our next step. Okay, so remember, you can kind of tilt your head, maybe close an eye and squint a little bit, and you can imagine now that this object is on the horizontal. All right. And then what we do is very similar. We imagine that these objects are moving in the same plane, so we can like swing these out and up, and then transpose our vector. So even though I haven't done it for the last few problems, I will do it for this situation here. So I have my string here, um, and I have my mass 1 here. So I'll make that a little nicer. Hey, that is not a square or a rectangle. Okay, so here's this M. That'll be corresponding to the one that's on the incline. And then let me just shorten this up a bit. And then I will have this identical mass over here. Okay, as before, we're going to transpose these. So this becomes mg directed in that direction. We have our tension directed in this direction. And just like all these other problems, these are all in the same string. So all of these tensions are the same. So no subscript needed just yet. All right, now we have a whole bunch more forces than we are used to dealing with. So I'll start with the ones that are in pink. So that is the normal force acting in this direction, and the force of friction that is acting in this direction. Now we have their green counterparts here. This is our FGY, and then this is our FGX. So we have these things all kind of worked out. All right, so a few steps that we have to take care of right now. We are saying it's moving up the ramp, so that means it's moving kind of in this direction. So that's the direction I'm going to call positive, and then here is down the ramp. So that's the direction I'm going to call my negative. I am now going to write my forces for each one of these, meaning I'm going to call this object 1, so I'll put a little 1 there, and this object 2, so I'll put a little 2 there. So now I can begin to work these things out. The sum of the forces on object 1 is going to be equal to the mass of object 1 times the acceleration of object 1. They have the same mass, but I'm going to leave it as M1 for right now, and we'll talk about why later, instead of just calling it just M. All right, so I'll just have to make sure I carry that through and have good bookkeeping so I don't screw anything up. All right, this is the positive direction. This is the negative direction as shown in my diagram. So that means for object 1, which again is this object, and this is object 2, I have a whole bunch of forces. First, I have a positive force of tension. That's this one right here. And then I have minus Fgx, and I have minus my force of friction. All right. Object 2 is a little bit easier to deal with. So the sum of the forces on object 2 is going to be the mass of object 2 times the acceleration, which doesn't need that. Oh, I'm running out of space here, so squeezing it in tight. We have mg and minus the tension. They're over on the side. So let me see if I can move these over just a little bit. And then I'm going to change their color just so it doesn't, maybe I'll make it even more different. I don't know. Yeah, like that. That is really hard to see. Just stick with this blue. Okay, so these two things are separate. Right? There's an imaginary line that runs right here. Okay, except it's not imaginary. There it is. Okay, so so we're in pretty good shape at the moment, except for the fact that we have the situation where this is made up of other stuff. This is made up of other stuff. And so we have to take care of each one of those things. So the first thing I'm going to do is I'm going to, over here, I would have my trig section. My trig section is going to indicate, well, sine of theta is equal to opposite over hypotenuse, and cosine of theta is equal to adjacent over hypotenuse. So this is h sine theta is equal to the opposite side, right? OP, right? And then h cosine theta is equal to the adjacent side. So substituting in those values, this is going to be my mg sine theta is equal to my fg x, and this is going to be my mg cosine theta, and that's going to be equal to fg y. Okay, respectively. And we've gone through that a bunch before. That really refers to this picture right here, where, as we've said before, this would be, of course, angle theta. So that's how we situate that triangle. So that's all well and good. Okay, and then additionally, sometimes it's useful to have, well, we don't need to worry about that. Okay, so now I have to deal with force of friction being equal to mu times normal force. All right, because this business right here takes care of, this FGX, but we still need to take care of the force of friction. So the force of friction is equal to mu times the normal force. And the force of friction is mu times the normal force. And as from the diagram, there are two forces in that direction. Now, if I'm on the AP exam, I would also write, well, the sum of the forces in the y direction must be equal to 0. I would classify those as my FGY and my normal force with my directions associated there. And I would say my normal force must be equal to my FGY. Okay, I will make sure I included that, which would then allow me to make the claim over here that this would then just be equal to, well, we could do it as two steps if we wanted to, FGY, and then that the force of friction, just written a little bit neater, is then equal to mu times mg cosine theta. Okay, so now we've got this term to substitute in and this term to substitute in up here. So I will do that. I'll do that now. This next line is now going to look like M1A is equal to the tension minus mg sine theta, substituting in that FGX, minus mu mg cosine theta. That's quite a bit. All right, and then we still have this other term up here because we still have multiple unknowns. All right, it is. What are we? Let me just make sure. We're solving for in both of these cases. We're solving for the acceleration. So just like before, I need to substitute into one in order to solve sort of for the other. So however you want to pursue that is what needs to happen next. So moving this down a little bit, it really doesn't matter. I'm usually preferential to solving for a positive tension, but it doesn't really matter. So I can solve this one up here by saying the tension up here is equal to mg minus m2. This is supposed to be an m2g. And I think I lost some ones and twos down there. Okay, so my apologies. I'll fill those in right now. All right, so over here, these should all have this should be a 2. This should be a 2. So we're good. We're good there. As long as we also put the 2 in right there. Oh, shoot. Oh, my gosh. These should all be 1s because it is object 1. So this should be M1, and this should be M1, and then this should be M1. Okay, and then 1s should follow through over here, and here is where the 2s are. Okay, so bookkeeping is important. That's obviously the kind of mistake that can really screw up your question. All right, just like before, we now need to do some substituting in. So I have my equation right here, which I'm going to rewrite, or in my case, duplicate, and give myself some space by moving that over. Okay, and now I need to substitute in these values. So I'm going to take this term and substitute it in for this tension right here, meaning I need to get rid of that tension. Hopefully that's all right, right? So that's where I substituted in. I put this in right there. So that's all good. I can drop these here. I don't need those, but that goes in there. And now we've got to kind of take a look around and see what we have. I have an A right here. Didn't mean to do that. So I can move that one over to the other side. These don't have an A in it, so in short order I can get the A's on one side. So let's go ahead and do that. This now becomes M1A plus M2A is equal to M2G. Make sure you copy correctly. Excuse me. Minus M1G sine theta minus mu M1G cosine theta. Okay. Because I have these situated as different masses now, I can't cancel these masses out. If I had these as written as like M and 3M or anything like that, I would be able to cancel out masses and I would just see relationships to one another. But for right now, I just have them as M1 and M2. So I will go ahead and write this as A is equal to M1 plus M2. All right, and then over here, there's nothing I can do besides pull out a G, which is not altogether useful, but I can go ahead and do it anyway. This becomes M2G, or excuse me, M2 minus M1 sine theta minus mu M1 cosine theta. All right, and then I can divide both sides by this term right here, and this now becomes A is equal to, all right, it's going to be this whole line right here, right, divided by this term M1 plus M2. What a mess. Okay, so for number 7, right? For number 7, we can do the following. So this is again a generalized version. But so now here I will go. There we go. So specifically now for number 7, what happens for number 7? For number 7, mu is equal to 0, so this term goes away. Okay, and for number 7, M1 is equal to M2. Right? Therefore, we can drop all of these subscripts. So kind of rewriting this, okay, we'll duplicate that, move it down here, and kind of finish some of this stuff off. So that closes up. Then we can get rid of all these subscripts. Gone, 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 gone. All right. If these things are equal to one another, then what do we have? We have A is equal to G M minus M sine theta, and down here M plus M, or in other words, I should just write this as 2M. Now we have an M in this term and an M in that term, which means we can pull each of those M's out. So this becomes Mg times 1 minus sine theta over 2M, which means that these M's can cancel out. And we can write our final line here being equal to G over 2 times 1 minus sine theta, and that would be our answer. Okay, and then for number 8, right, we would still come up and we still have this line all kind of squared away. And actually, I'm going to go back to this line. Is this the line I want to go to? Sure. I'll go back to this line for number 8 for not for no real reason, but so for number 8, we'll do that in that same color. For number 8, like before, we're saying M1 is equal to M2, and we're saying that mu is greater than 0. So in this case, I would, like before, I would cancel out. I'd be able to cancel out all these m's without the algebraic step I did before. But so we've got that. It looks like I lost a little bit of this over on the side, but I'll take care of that. An m in each term allows us to cancel out all these m's. This now becomes 2a over here is equal to g minus g sine theta minus mu g cosine theta. G in each term and a 2 over here allows us to write g over 2. Okay, we can pull out. Yep. Becomes 1 minus sine theta minus mu cosine theta, which is the same answer that we had above here, except with the addition of one extra term right here, which, you know, makes sense in terms of the acceleration, that our friction, the portion contributed from our friction, would just reduce this acceleration just by this constant factor just a little bit more. It takes away just a little bit more. And it makes sense that if we were to have a coefficient of friction of 0, right, then this whole term here would go away, right? So that would go away, and that makes sense. So again, we get back immediately the same problem that we had above, or the same acceleration that we would have had before. Okay, so that's good. We're on. It seems like these kind of checks makes us pretty sure we're on the right track. And then and so that's our answer ultimately. And that's our final form best answer. What we can do is then try to say, okay, well, what about for the situation where well, we just kind of mess around. So like this is the answer, or rather this is the scenario that we have. Right? We have a block on a plane, and that block is attached to a string, and then we have a mass, and this situation is defined by this angle theta. Well, what if we were to increase this angle theta all the way up to 90 degrees? Well, if we were to increase this to 90 degrees, right, if theta were to be equal to 90 degrees, what would that mean? Well, we know from looking at these situations before, right, that when theta is equal to 90 degrees, we would expect the normal force, or as theta approaches 90 degrees, we would expect the normal force to be equal to, or to approach 0. Because when we look at these components, right, looking back at this trig up here, for the cosine of 90 degrees, that term is equal to 0, which means our FGY is equal to 0, which means that our force of friction should also be equal to 0. We also know that for when we approach 90 degrees, the sine of 90 is 1, which means we would expect our FGX to be equal just to mg, right? mg sine 1, or mg sine 90 would just be mg times 1, so mg. Okay, so why are we going through that? Well, because when this approaches up to 90 degrees, that is very similar to or in fact, we're able to claim that it is the same as the scenario that these two blocks are just hanging like this, right? Because this surface that's here, right, that this block on the left is sitting on, is just a vertical plane. It means that the normal force is equal to 0, so we can just consider it to look like this. Why is that important? Well, for that scenario, we need to know what that acceleration would be. And if we have two objects of equal mass on either side of a pulley like this, we would expect this acceleration to be equal to 0. So for 90 degrees, we would expect that the normal force would be equal to 0. And therefore, we would also expect, right, that the acceleration would be equal to 0 because they'll be pulling the same amount down on both sides. So does that check out with this scenario right here? All right, we can substitute in those values. The acceleration of g over 2, all right, is going to be 1 minus the sine of 90 minus mu cosine of 90. So as we said before, this term goes to 0. And this is the term that is contributed by friction. So we would expect that to be 0 at this angle for the reasons we've already stated. We already said then that sine of 90 is equal to 1. If not, you can check it in your calculator, right? And then we have this scenario. So we have this whole term here being equal to 0. 1 minus 1 is 0, so we have 0 minus 0. And then it doesn't matter what we multiply it by out front, we're going to get that we have an acceleration equal to 0. So once again, we have a check. We have a check there. Okay, so that's most of those problems. The exception is number 6. Number 6 requires you go through a problem or a thought process similar to what we have done, in this area right here, where you say, okay, what would happen if, right? Well, what if it was like this? You can also substitute in some different values and for m or different ratios for values and see what that does. So for example, in number 6, you can say, well, m1 is equal to m, and m2 is equal, and again, this is for number 6, m2 is equal to, it becomes really small, 1 over 100 m, right? And then see what that gets you. How does that change the scenario? That would be the mathematical way to approach that. Okay, so hopefully these things are helpful, and see you soon.